Slide 1. In the name of God, the most gracious, the most merciful. Slide 2. 1. Good behavior, the concept of rationality. In artificial intelligence, good behavior means that an intelligent agent can act in its environment in a way that achieves specified goals or maximizes rewards from the environment. To evaluate this, we need a performance measure that assesses the agent's actions to determine if it is performing well. This is where the concept of performance measures comes into play. Slide 3. 2. Performance measures. These measures are precise, measurable, and aligned criteria used to evaluate an agent's performance. They play a key role in guiding decision-making and enhancing agent design. Characteristics of performance measures. Precision, clearly defining measures to avoid ambiguity. Measurability, enabling numerical or qualitative assessment of performance. Alignment with goals, reflecting the true objectives designed for the agent. Slide 4. Examples of application. Agent performance measures. Smart vacuum cleaner, clean surface area percentage, energy consumption, task duration, non-damage to surroundings. Autonomous car, safety, no accidents, adherence to driving rules, fuel efficiency, passenger comfort. Virtual assistant, answer accuracy, response speed, user satisfaction, privacy compliance. Key point. Integrating measures is essential. For example, in autonomous cars, speed and safety might conflict. Thus, the performance function must balance these measures. Slide 5. 3. Rationality. Rationality refers to decision-making and actions based on available information, resources, and environmental conditions to achieve the best possible outcome. Difference between rationality and perfectionism. Perfectionism, achieving the best performance without considering real constraints. Rationality, optimizing performance under real conditions, acknowledging uncertainty and limited information. Slide 6. Features of a rational agent. A rational agent must possess 4 key features to perform optimally in dynamic and complex environments. 1. Awareness of the environment. The agent should be capable of gathering and analyzing environmental data to make informed decisions. Tools, sensors, cameras, GPS, temperature/pressure sensors, data processing, and AI techniques, e.g., image recognition, natural language processing. Example. Autonomous car uses cameras and LiDAR to gather information, e.g., obstacles, road lines, or traffic signs. Virtual assistant recognizes user requests through voice analysis, e.g., today's weather, or set a reminder. 2. Knowledge-based decision-making. The agent makes decisions based on existing knowledge, collected data plus learning algorithms. Challenge, decision-making under uncertainty, e.g., predicting pedestrian movement by an autonomous car. Example. Robotic vacuum cleaner stops cleaning upon detecting wet floors to prevent motor damage. Film recommender system suggests similar movies based on the user's viewing history. 3. Adaptability. The ability to adapt to sudden or long-term changes in the environment. Tools, machine learning, evolutionary algorithms, and continuous knowledge updates. Example. Rescue robot finds alternate paths if the main route is blocked due to collapse. Virtual assistant improves performance by learning user preferences, e.g., preferred time for receiving news. 4. Performance optimization. Maximizing performance measures, e.g., speed, safety, or user satisfaction, while considering limitations, e.g., energy or time. Methods, optimization algorithms, e.g., genetic algorithms, simulated annealing, and objective functions. Example. Autonomous car balances 70% safety and 30% speed in its performance function. Home energy management system optimizes electricity consumption based on real-time pricing and user priorities. Slide 7. 4. Key challenges in performance measures. Designing performance measures for intelligent agents involves several challenges. 1. The first challenge is defining what constitutes the right action. In the realm of artificial intelligence, we adhere strictly to consequentialism. For instance, an AI cannot, in response to your consistent refusal to follow a navigation system while driving, go offline for a few minutes to compel you to use the recommended route. 2. Humans, as autonomous beings, pursue their own preferences and desires, which is why they have varying performance criteria. For example, a wealthy individual might be deemed successful, but in the pursuit of material possessions, they might disregard many human principles. Similarly, a scientist might be considered successful but could have distanced themselves from family interactions, quality time with children, and other benchmarks of a well-rounded human being.
3. Performance outcomes do not always encompass all performance criteria, as the process and tools are also important. For instance, a smart vacuum cleaner aiming for maximum performance, measured by the greatest amount of dust removed in a given time, might produce waste in the process. This waste could involve redistributing the collected debris into the room. 4. Who defines the philosophy of performance criteria? Should it be those who advocate for a secure, monotonous life, or those who accept a life without risks, challenges, or unpredictability? Which is better, an economy where everyone is moderately poor, or one where a few are wealthy and many are impoverished? 5. Lastly, how irreversible or dangerous can the consequences of defining a performance criterion incorrectly be? King Midas is a fitting example from mythology. He wished that everything he touched would turn to gold. However, this wish became a curse when he accidentally turned his family into gold by touching them.
Other challenges include balancing conflicting goals. Example, in rescue robots, speed and energy efficiency may conflict. Performance functions can prioritize 60% speed and 40% energy saving. Environmental uncertainty. Example, self-driving cars must handle sensors' errors in rainy weather by utilizing historical data for decision-making. Dependence on initial knowledge. Example, fraud detection systems may underperform if training data lacks complete fraud examples. Limited knowledge. Example, autonomous cars lack full environmental information, e.g., obstacles behind a truck. Learning curve. Example, robotic vacuum cleaners may initially follow inefficient paths but improve through reinforcement learning. Autonomy. Example, autonomous medical injectors should function independently but alert doctors in case of unforeseen errors. Slide 8. 5. Conclusion. Performance measures and the concept of rationality are fundamental pillars in designing and evaluating intelligent agents. These measures not only assess success in achieving goals but also play a key role in guiding intelligent decisions and optimizing performance. However, their design involves challenges such as conflicting goals, environmental uncertainties, knowledge limitations, and dynamic learning. Rational agents with capabilities like environmental awareness, adaptability, and knowledge-based decision-making tend to perform better in real-world conditions. To achieve this level, performance measures must be designed to meet both short-term objectives and long-term adaptability. Slide 9. 6. Practical suggestions for improving the design and evaluation of intelligent agents. To overcome challenges and achieve effective rationality, the following suggestions are proposed. Combining performance measures with a multidimensional approach. Employ composite objective functions to balance conflicting goals with appropriate weighting, e.g., 70% safety and 30% speed in an autonomous vehicle. Use multi-criteria decision-making, MCDM, methods to prioritize measures. Example, in a robotic vacuum cleaner, the performance function can be a combination of percentage of cleaned area, energy consumption, and execution time. Using adaptive algorithms and machine learning. Apply reinforcement learning to progressively improve performance in dynamic environments. Use uncertainty prediction models, e.g., Kalman filters or Bayesian networks, for unpredictable environments. Example, a movie recommender system can provide personalized suggestions by learning from user behavior. Interaction between autonomy and human oversight. Design systems that operate autonomously in most cases but seek human assistance during critical conditions, e.g., errors or severe uncertainties. Utilize transparent user interfaces to collect user feedback for agents. Example: a virtual assistant can ask the user, "Was this response helpful?" after completing a complex task to improve its accuracy. Long-term evaluation and benchmarking against standards. Compare agent performance with industrial standards or reference benchmarks, e.g., ISO safety standards for autonomous vehicles. Conduct stress testing to evaluate performance under worst-case scenarios. Example: testing autonomous vehicles in harsh weather conditions, heavy rain or snow, to assess sensor limitations. Considering ethical and social dimensions. Define measures that ensure privacy protection and avoid bias in agent decision-making, e.g., in intelligent hiring systems. Use interpretable algorithms, explainable AI, to enhance decision-making transparency. Example: a credit assessment system should include measures like no racial or gender bias in its performance function. Continuously updating measures. Use feedback loops to adjust performance measures based on environmental changes or user needs. Create collaborative platforms involving designers, users, and AI ethics experts. Example: in a virtual assistant, the priority of the response speed measure can increase during emergencies to meet user needs. Final summary. Intelligent agents can only achieve true rationality when performance measures align with practical challenges, technological limitations, and societal expectations. This alignment requires a combination of technical innovation, in-depth data analysis, and attention to ethical dimensions. By adhering to these suggestions, agents can be designed to be not only efficient but also trustworthy and socially compatible. Slide 10. A heartfelt thank you. Thank you so much for your time and attention to this presentation. AI Commander Alireza Khoshzaban, hope I've been able to illuminate part of the path in the roaring sea of artificial intelligence and offer some small assistance in your academic journey.